Welcome to this NPTEL course on robotics, basics and advanced concepts. In this week, we are looking at application of parallel robots. This is the second lecture in this week, and in this lecture, we will look at Stewart platform manipulator as a sensor. Okay, so quick acknowledgement, this work was done by Dr. R. Ranganath, who was a student from ISRO, and Dr. Sandipan Bandyopadhyay, he is a faculty member at IIT Madras. So the contents of this lecture are the following. We'll first introduce the Stewart platform again. Then we'll look at the statics of a 6-6 Stewart-Gough platform. Then we'll figure out how to obtain the singular configurations in a 6-6 Stewart platform. Then we will look at the design of a 6-component force torque sensor based on a Stewart platform in a near singular configuration. Then I'll show you some experimental results and conclude this lecture. So the Stewart-Gough platform, or the Gough-Stewart platform, was first used as a tire testing machine in UK. Okay, it was invented by Stewart in 1965, and later on it was found that Gough had invented this much earlier. So the modern usage is Gough-Stewart platform. So in a Stewart platform, there are 6 legs which can be extended. Okay, so each of these legs are actuated. So it turns out that the Stewart platform has 6 degrees of freedom. So this is the original picture of the tire testing machine by Stewart. So basically we have a top platform, and there is a tire which is mounted here, and then there are these 6 legs which can extend. Okay, so as you extend these 6 legs, this top platform can tilt, do roll, pitch, they can also do linear motion along XYZ axis, and hence if this tire can be tested by rubbing, by pressing, by doing various things with some equipment at the floor. So this linear motion along X, Y, and Z and the rotational motion along X, Y, and Z are also sometimes called heave, surge, and sway, and roll, pitch, and yaw. Okay. There are many modern uses of Stewart platforms now. So initially the tire testing machine is now used for material handling. A Stewart platform can also perform very fine or micro motions. Okay, Stewart platform is a parallel device, hence the errors are expected and shown to be smaller than a serial manipulator with the same degrees of freedom. Okay, in a 6 degree of freedom Stewart platform, the error is the maximum of the errors in each of these legs. The errors do not add up as in a serial robot. It is also used in many industrial manufacturing setups. It is used for precise alignment of mirrors, and it has also been proposed, this is of course a schematic of a Stewart platform being used for surgery. The most popular and famous use of a Stewart platform is the flight simulator. So basically a Stewart platform can support a platform at 6 points. Hence it can carry a large amount of load, okay, because the whole weight of this top platform is supported at 6 places. The top platform is like a cabin with audiovisual display, and a pilot or a trainee will be sitting inside this cabin with lots of audiovisual displays around it. And then when you move the joystick or the controls of an airplane, this top platform can move in those 6 degrees of freedom. It can do XYZ translation and roll, pitch, yaw. So hence, depending on what is projected on those screens, you can be trained to fly an aircraft. So this is one of the most common uses of a Gough-Stewart platform as a flight simulator. The kinematic model of a Stewart platform consists of a top platform, which is this with a coordinate system P0 attached to the top platform, typically at the center. Most of the time this top platform is like a hexagon, equal sided, and at the top platform there are these spherical joints P1 through P6. There is also a bottom platform which have U joints or hook joints, which are B1 through B6. Okay, so the connection between the top and bottom platforms are through legs. Okay, so for example, here the leg is connected like B2, P6. Okay, where the leg consists of a prismatic joint which can change its length. Okay, there's a fixed coordinate system B0, and as you actuate these legs, the top platform can do this 6 degrees of freedom. Okay, so here is a video of a Stewart platform simulation which was done using the software called Adams. So as you can see that these leg lengths are changing, and then because the way you are changing the leg lengths, you can move the Stewart platform in various ways. So this is some kind of motion where some legs are being moved. So these are basically individual motions of along X, Y, and Z and the combined motion. So the Gough-Stewart platform can also be used as a sensor. Okay, so basically when it is used as a sensor, it can measure the 6 components of the forces and torques which are acting on the top platform. So if there is a force with components Fx, Fy, Fz, and a moment or torque which is Mx, My, Mz, it can be rigged up to sense or measure these forces. So when it is used as a sensor, these actuators are locked. So when you lock the legs of the actuator, the whole thing becomes a structure. And instead of applying force at the actuators or cylinders, strain gauge based sensors are mounted there. So they can measure the strains due to the load which is acting on the top platform. Okay, so essentially the external applied force moment at the top platform can be sensed at the legs. And we'll show a little bit of the mathematics. So consider a single leg of a Stewart platform. So basically we have a fixed coordinate system B0, a top platform moving coordinate system P0. Each of these S joints can be located by a vector P0 Pi. Okay, so Pi is this point of the spherical joint. The U joint can be located by a vector B0 Bi, Bi with respect to B0. This is a fixed coordinate system. And then each leg can change its length by Li. So the Z axis is along the direction of the joint like any other joint. And then we have these two U joints, two rotary joints which represent a U joint. So the U joint is nothing but rotation about X and Y. Okay. So the position vector of any S joint, okay, can be written as B0 SI, so with respect to the fixed coordinate system, as some vector P0 Pi pre-multiplied by a rotation matrix, because this vector is in the moving top platform coordinate system, plus this translation from the fixed origin to the top platform origin minus the location of the U joint. Okay, so this is the basic equation for the Stewart platform for each leg which locates the spherical joint. The length of the motion, okay, Li, is along the prismatic joint, and we denote a vector which is BSI, which is B0 SI. This is the unit vector along this prismatic joint in this form. So this is B0 SI divided by Li. And you can show that the force and the moment which are acting on the top platform, denoted by F tool and M tool with respect to the B0 coordinate system, must be equal to the force which is acting along this unit vector along each length and the moment of this unit vector and the force which is acting along the Bi cross B0 SI. Okay, because the Stewart platform is in equilibrium, all the joints are locked. So we can rewrite this equation as B0 F tool. F tool is the force and the moment acting on the end effector as some matrix H into F. So F are 6 of them. So there are these 6 legs. Each of them are applying a force along its length. So we can rewrite it this way. And the elements of this H matrix are nothing but the unit vectors along this leg and the moment of this unit vector with respect to the B0 fixed coordinate system. Okay, so the first column is B0 Si, then B0 B1 cross B0 S1 and so on. So eventually what we can write is that this F is H times F. We can also invert this H matrix and write F as inverse of H into F comma M. Okay, so this is the starting point of a Stewart platform based 6-component 4-stalk sensor. So from this basic formula, we can see that this matrix H depends on the chosen geometry. What is the connection point between the top and the bottom platform? Okay, this quantity F semicolon M is actually not really a vector, just like in any parallel robot. Okay, just like in when you are discussing force and moment together, it is a combination of 3 components of force and 3 components of moment. And this F on the left hand side are the axial forces in the 6 legs. So if H were isotropic, meaning if the eigenvalues of H were all equal, okay, all components of F comma M will be equally sensitive. Okay, we can measure this F and we can see that all the values of the small f vector will be equally same. If H is singular, certain components of this F comma M will give rise to larger small f. Okay, and this is what we mean by a Stewart platform in a singular direction. Okay, so if it is in a singular configuration, then some f and some m will give rise to large or infinite f. If it is a near singular configuration, then it will give you large small f. Okay, and we can compute these directions, and in these directions some amplification will be happening as compared to the other directions. So there was a work by Professor Bandyopadhyay. He obtained the singularity manifold of a 6-6 Stewart platform, okay, in a regular, semi-regular configuration. And he showed that the Stewart platform singularities lie on this curve, which are basically quadratic in the xy plane, okay, and cubic in the z direction. Let's look at the singular configuration of a Stewart platform in a little bit more detail. So we will start with the Stewart platform where the top and the bottom platform are of the same size. Okay, so P1, P1, B2, P2, B6, P6 and all these things. So the connection points are on a hexagon. The bottom points are also on a hexagon and the sizes of the hexagons are same. Okay, so the bottom platform points are denoted by BI, the top platform points are denoted by PI, and the leg connection can be denoted by a combination BI, PJ. Okay, so as we combine them, we can find the vector along the leg and the moment of the vector along the leg, and then we can form this H matrix for any different combinations or any different configuration which we can think of. Then we find the eigenvalues of this matrix. So for example, if B1, P1, B2, P2, B3, P3 and so on, what does this mean? That each of these legs are exactly vertical. Why vertical? Because the top platform and the bottom platform are exactly of the same size. Okay, they are both hexagons. So if all these legs are exactly vertical, you can show that there are 3 zero eigenvalues. And these 3 zero eigenvalues of H corresponds to singular directions, corresponds to Fx, Fy and Mz. Okay, so what does it mean? That if I apply a force along Fx, Fy or Mz or moment along Mz, it cannot be resisted. Okay, remember the H transformation matrix we had discussed in parallel robots. It shows you the directions in which the force cannot be resisted. So if you apply a very small force, it gives rise to a very, very large small f in this when the forces are in the singular directions. Okay, so why large? Why not infinity? Because you can never make these legs exactly straight. So the eigenvalues can never be exactly 0, or the determinant of h can never be exactly 0. So if it is small, then it is near singular configurations. Okay, this is another configuration which you can see. It is B1, P2, B2, P1. So basically the legs are crossed. Two adjacent legs are crossed. So B3, P3, B4, P4, and then all the other legs are straight. So first two leg connections are crossed and all others are straight. So in this case, you can see that the eigenvalues of h, there are two of them which are 0, and they correspond to singular directions which are fx and mz. Okay. If you cross all the legs b1, p2, b2, p1, b3, p4, b4, p3, b5, p6, b6, p5, then none of the eigenvalues are 0, and hence there are no singular directions. We can also find, if you do from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to 1. So basically each of the legs are shifted by 1. Then you can see that there are singular directions which are mx, my, and mz. Okay. So one next important thing for fabrication of a four-stalk Stewart platform is this: how we can get rid of this spherical joint and the hook joint. Why do we need to get rid of the spherical and the hook joint? Because in an actual kinematic joint there will be friction. Okay, so not only will the leg force be amplified at a near singular configuration, but even the friction at the joints will be amplified. So we need to somehow get rid of these forces in the joints, at the hook joint and at the spherical joint. So what we do is we make what are called as flexural hinges. So a flexural hinge is nothing but you take a rod, okay, and then you make, at some place you cut it such that the connection is like two cones. Okay, so it is like two cones meeting at a point. So the top part of the leg can move with respect to the bottom part of the leg because the section is very, very thin there. So it basically deflects. So it is not really a physical joint, but it will deflect, it will deform. But as a sensor, we don't need too much motion at the joints anyway. Okay, so sensor is normally a rigid or a semi-rigid structure which do not deform a lot. So in this way, we can make sure that the top platform will move with respect to the bottom platform without the effect of the friction and other problems associated with the spherical joint. Okay, one of the problems in joints is there is something called hysteresis. Okay, here also there will be some hysteresis. So depending on how it is moving, you will slowly see that for a given force, while loading and while unloading, the deformations are slightly different. That is a property of a material. However, by careful choice of material and heat treatment and other things, we can make sure that this hysteresis is very small. Okay. We also made a CAD model of this sensor where all the legs are exactly straight. So B1, P1, B2, P2, and so on. And the reason is we have these small flexural hinges and we need to make sure that they do not break or they do not fail when certain loads are applied. So this is the model of this 6.6 Stewart platform which is made in NISA and analyzed. Finite element analysis was done in NISA. So basically these are the top platforms. This is the bottom platform. And then there are these flexural joints connecting each leg to the top and bottom platform. And as I said, we do not have sliding joint. We do not have actuators there. So instead of an actuator, we put a ring which can measure the strains or the deformation in each leg. So basically the ring looks like this. So this is the top part of the leg, this is the bottom part of the leg. So if I apply a load along this leg, okay, at the mid plane you will get the largest strain. At the mid plane you will also get the largest stress. Okay, the deformation is more, but the stress is more at the mid plane. So we will put some strain gauges, 4 of them, one outside surface, one inside surface of this ring on both sides, and then we use this strain gauge in a full bridge configuration to measure the strains when some axial load along the leg is applied. Okay, so we checked all these calculations, we did this finite element analysis, and we showed that the 1 meter strain on these legs and at different parts of the Stewart platform were well within the tolerance or well within the acceptable limits. So this Stewart platform was built. As you can see, it is not very big. It is similar to the size of a pen with 6 legs. And then there are these wires which are connected to the strain gauge, and then we take these wires to a strain indicator. So then we apply some known loads on the top platform. Okay, so if you apply a known force on the top platform, okay, which is this applied external force, and then you measure the strains in each of these legs, and from the strains we find out what is the force in each of the legs. Okay, how can we do that? We do some calibration. We apply a known force of so many newtons, find out what is the strain in each leg, and then we can have some sort of a table which tells you this force corresponds to this Fi. So what you can see here is when you apply Fx and Fy, the output in each of the legs, so this is leg 1, 2, 3, 4, 5 and 6, this is the force measured in each of the legs. It is much larger than when you apply only Z. Okay, does that make sense? Yes, because the configuration is very close to singular configuration where the sensitive directions are Fx, Fy and Mz. Okay, so a small f will give rise to a large leg force. Okay, whereas the Z there is not much amplification. Okay, the Z force, the vertical force, is also supported at 6 places. So hence it is very small. Okay, so we get an amplification of the order of 6. Okay, so 1 Newton force applied along the X or the Y direction will give rise to some force which is 6 times if you had applied the force along the Z direction. We also applied some moments on the top platform, and again you can see that this MZ direction is more sensitive as expected. So we know the Stewart platform with all the legs exactly vertical is sensitive to Fx, Fy and Mz, and these tests show, or these results show, that is indeed true. Okay, so you can see that the slope of the Mz which is applied by leg is much larger than Mx and My. Mx and My are both very close to the horizontal line. Okay, little bit more, but not much. Once we have this proof of concept that we can indeed measure Fx, Fy and Mz more sensitively, then we form that H matrix, again using some calibration. Then we find the inverse of the H matrix, okay, and then we do some real tests. So for example, if you apply Fx and Fy of this value 0.093, 0.093 and so on, and similarly some Fy, Mx and My, which are these two values, we can do a finite element analysis and find out what should be the leg forces, okay, which are these. And then, we can find out the leg forces, and from the leg forces we can compute what should be the forces and moments which the device is measuring. So the finite element analysis is telling you that we apply 0.093 and the analysis is telling you 0.0942, 0.093, and this is 0.898. Instead of 0, we are getting 0.095 and so on. Okay. Likewise, we can also perform this actual test and you can compute what the force it is measuring, and it turns out it is 0.945, 0.0899 and so on. So as you can see, it is reasonably close. We know this is what we have applied, and this is what we have measured, and this is what we have computed using the finite element software. All are sort of close. Okay, this MZ is not really close because this is minus 0.14, whereas it's supposed to be 0. Okay, but nevertheless, it is not too bad. If you apply Fx, Fy, and Mz together, so we are applying 0.093 and some Mx, My, and Mz. What we can see, the finite element is telling you analysis is that these are the values which you should get from computation. The test is telling you these are the values which you should get. Test means you measure the leg forces and you multiply by the H matrix, which you now know. Okay, and then you get the measured forces. So as you can see here also, it's not too bad. It is quite reasonable. Okay, so this shows that the 6-component force torque sensor that we have fabricated can indeed measure external forces and moments. Okay, and more importantly, it can measure very small values of Fx, Fy, and Mz. It is more sensitive to Fx, Fy, and Mz. We also built another prototype where the legs were shifted one. Okay, remember 1 goes to 2, 2 goes to 3, 3 goes to 4, like that. And for that configuration, I showed you that the Stewart platform based force torque sensor would be sensitive to Mx, My, Mz. Okay, here also we made these hinges, flexible hinges. This time it is slightly different. It is not like a cone, 2 cones touching each other. However, here it is like 1 degree of freedom cuts. Okay, but this is 90 degrees to each other. So there is one actually at the connection between the top and the bottom platform. There is a thin plate, 2 thin plates which are perpendicular to each other. Okay, so it is the connection point is not like a cone. Okay, like 2 cones meeting. And this helps because this can carry much more load. So this Stewart platform was also built. Okay, it could measure forces up to 50 newtons in the X, Y, and 200 newtons in the Z direction with a sensitivity of 0.5 newtons. It could measure moments up to 10,000 Newton millimeter with a sensitivity of 50 Newton millimeter. Okay, this is a sample plot or a calibration plot of strain versus moment. So we can apply a moment My and we can measure the strains, and this is what it looks like. So it is fairly linear. So this is also one of the requirements for a typical sensor, that we would like the sensor to be linear. So if you double the moment, the strain should more or less double. And likewise reduce if you reduce the external force or moment. So in conclusion, the Gough-Stewart platform is a very versatile device. Okay, it can be used in a wide range of tasks. It can be used for tire testing originally. It can be used for orienting a mirror. It can be used for various things in industry for manufacturing. One of the most common uses of a Stewart platform is for flight simulators in aerospace industry. In this talk or in this lecture, I have showed you that the Stewart platform can also be used as a 6-component force torque sensor. Moreover, we have used this Stewart platform in a near singular configuration such that we get very high sensitivity along the singular directions. And I showed you 2 prototypes which are built, calibrated and tested.